Okay, we're on the third podcast. I was talking about gravity gradient, and I promised to move on to permanent magnet. But I want to make yet another point about gravity gradient. It's a spring and a mass. The spring is that the gravity gradient wants the maximum moment of inertia axis to be perpendicular to the Earth. Or, if you want to, that's a very complicated way to put it. It wants the boom to be pointing straight up and straight down. Or it wants the 3U CubeSat to be vertical, the long end going up and down, right? So that's the spring. And then you have a mass. You have, the satellite has a certain moment of inertia. And so given that torque, it will develop a certain frequency or a certain angular velocity. And you can model that or whatever. So the thing is going to swing. It's going to pendulum. It'll look just like a pendulum in orbit. And nothing will damp that pendulum. It will just keep pendularizing forever. And how big it is depends on how tight the spring is, how much gravity gradient torque you've got. So if you're closer to the Earth where the omega is higher, that you'll have a tighter spring. And so the amplitude of the pendulum will be less. And if you're up in geo trying to do this, assuming there's no other torques on you, it's going to be a very big oscillation because the spring is very weak at geo because the omega is, much, much smaller, 24 hours instead of an hour and a half. So it's 16 times smaller squared, right? So, it's almost a couple hundred times smaller, which means your amplitudes are going to be bigger. But the good thing is that that's not rotation. That is a pendular motion. So you could have liquid in a tube damping. And many people have done that, and it works, right? So you just have 3 tubes with some viscous liquid in them that isn't going to freeze, preferably. But we don't really like to do that because it could leak, it could freeze. NASA's not going to like the liquid you pick because it's toxic or it can blow up or who knows what it is. We mostly don't do that. We mostly do something called magnetic hysteresis damping. And magnetic hysteresis damping is that it's so simple that it almost seems like magic. You have a soft iron, meaning pure iron, and you heat it up so that the molecules of, the atoms or the crystals are randomly distributed. So there's no net magnetic field in the iron. It's been, heat treated to be that way. What happens when you take a totally isotropic piece of iron and put it in a magnetic field? It becomes magnetized. But if you put it in an opposite magnetic field, it magnetizes the opposite way. That's the core of a transformer, iron core of a transformer. What happens to the iron core of a transformer? It gets hot. Why does it get hot? Because we're forcing its magnetic field to go from north at the top, south at the bottom, to south at the top, north at the bottom, and cycling that 60 times a second. And every time you flip all those magnetic dipoles, you dissipate a little bit of energy. And that little bit of energy that you're dissipating manifests as heat. So what's really happening with a transformer, the energy coming out of the transformer, let's say you're going from 110 volts to 220 volts because you got a, gadget. I have one in my apartment here in Rome that goes from 220 volts to 110 volts because I brought over a piece of electronics that only turns out, the manufacturer said it would run on 220, but in fact it's placarded against it. It's do not attach to 220. So I went hunting all over Rome and found a transformer that goes 220 to 110. Apparently I'm not the first person who brought something over from America and had that problem. And the thing about it that's interesting is if I'm using that amplifier for a long time, the transformer gets hot. It's like, yeah, I know this, right? Right? So what that's really telling you is that it's pulling energy out of the system. Okay, so put that piece of iron on your satellite, and every time that piece of iron gets the magnetic field swaps in it, it's going to pull a little bit of energy out of that rotation. Let's say the satellite is flipping itself end over end over end over end. That magnetic magnetic hysteresis rod is going to have to change its magnetic field orientation of all its little dipoles. And when it does that, it will heat up just a little tiny bit, and that will take energy out of the rotation. So, in fact, just changing it a little bit, increasing the magnetization, decreasing, you don't have to go all the way north to south. You don't have to flip it. You just have to increase it, decrease it, increase it, decrease it, increase it, decrease it. Every time you go around that loop, where you increased it, increased it again, you will lose a little bit of energy, and that's the hysteresis loop of magnetization. When you magnetize something and demagnetize it, or you magnetize it partially, and then you magnetize it more, and then you demagnetize it to the partial state again, you will lose energy in that process. As second law of thermodynamics, you have to lose energy in that process. Where does that energy come from? From the rocking. And you can calculate how much energy that is and how long it will take to damp the motion. Now, obviously not to zero. You're going to go 1/2, 1/2, 1/2, 1 over E, 1 over E, 1 over E. But the point is, just like the inexorableness of gravity gradient torque itself, the inexorableness of that dissipation. And the nice thing about hysteresis rods, you don't do anything. You just, students have asked me, how do I attach this? Like, however you want to, nail it on, glue it on. It doesn't matter, because it's the intrinsic property of the iron that's causing that to happen. So usually these are long rods, because you get the effect more when the fineness ratio is very great. So you make like a half a centimeter, a quarter centimeter diameter rod, 10 centimeters long in a 1U CubeSat, or 9 centimeters long. Put one on each axis, X, Y, Z, and you're basically done. So the damping of gradient torque is highly efficient. And actually we put those same little rods, because they basically cost nothing, weigh nothing, and do nothing. You don't have to control them or anything, on many satellites. That way, if they get kicked off the launch vehicle asymmetrically for whatever reason, eventually that rotational motion will be damped out, because you're causing the magnetic, if you're in low enough Earth orbit that you have magnetic field, which means, up to about 1,200 kilometers, this will work. Above those altitudes, the magnetic field is so weak that it won't work. And it's really a shame, because when I worked on the lunar CubeSats, no magnetic field there, Guy. So you can't use magnetic stabilization. You can't put a magnet on it, and you can't use hysteresis rod damping. What a drag. It's much harder to do that, because we use that so much in our terrestrial systems. Okay, we pretty much burned a hole through slide 17, so let's go to slide 18, permanent magnet, right? This is like the dream solution that everybody, immediately gets drawn to. And, I'm really frustrated, because I feel like I picked a set of slides that do not have all of the pictures on them that I want. And at this point, I don't think I'm going to change it. So, we'll look at the permanent magnet for a second. And I'll just have to describe it in words. I did make a slide, but I'm not seeing it in this set. Okay. You've got, as you can see in my kind of grainy drawing that I stole from my first book that I published in 1995, and it wasn't this big in the book. You have a satellite, it's just a cylinder for arbitrarily, with a magnet in it. And what's the magnet going to do? It's going to point, the south is going to point at the North Pole, and the north is going to point at the South Pole. And we tend to think, with our simple-minded model of the Earth's magnetic field, fantastic, right? But what you forget is a couple of things. One is there's no damping, right? And you think, well, Rick just told me I can use magnetic hysteresis rods damping. Well, maybe, but you've got a big friggin' magnetic field. Big. I mean, this can be a little tiny magnet that weighs an ounce. But if you're talking about overcoming gravity gradient torque, it don't take much. So you do that calculation. How big is the gravity gradient torque? I want to be 100 times bigger with this magnet, and then I'm done. You're not done. Because if the magnet is that strong, it will saturate the magnetic hysteresis rods, and they won't even notice that the Earth's magnetic field is changing. So you can risk wiping out the best damping that you could have gotten. And mostly magnetic stabilized satellites do not have damping. It's unfortunate, but that's the way it is. Okay, so they tend to wobble a little bit, but then you'll figure, well, I'll make the spring really tight, I'll make the magnet really strong, and the satellite will not wobble, right? And you're right about that. It won't wobble. It'll wobble. I mean, according to physics, it has to wobble. It has to oscillate back and forth around the set point, but not much. We don't see, you see a little bit of wobbling in a compass on the Earth because the Earth's magnetic field is weak and the compass, it oscillates back and forth around the needle pointing exactly at north. Okay, you don't care, right? It's not that big of a deal. What is a bigger deal is that the Earth magnetic field is not parallel to the surface of the Earth. You know what it looks like. It touches the Earth in Canada, and it touches the Earth someplace in the South Atlantic, and or South Indian Ocean or whatever. Unfortunately, being a North American, I know very well where the North Magnetic Pole is, but I don't know where the South Magnetic. Maybe if it's in Antarctica, I really don't know. But anyway, when it goes over the North Pole, if you're in an inclined orbit, if you're not in an equatorial orbit, the whole satellite's going to flip over as you approach the pole. It's going to be parallel roughly at the equator. The magnet will be parallel to the Earth's surface. When you get over Canada someplace, it's going to be pointing straight down. When you get over Siberia, it's going to be pointing backwards, from where it was when you were over Hawaii. And so the satellite is actually flipping itself over one complete rotation every orbit. Maybe you don't care. But anyway, it's something to keep in mind. So a permanent magnet works great if you're not near the poles, where the Earth's magnetic field is fairly parallel to the Earth's surface. So, if you put a satellite in a low inclination orbit, like 28 degrees, which is the inclination you'll naturally get if you don't do anything and you launch from Kennedy, because Kennedy's at 28 degrees. So, from 28 degrees on down, great. But if you have a launch, and our launch is coming from Kennedy, so maybe it'll be that, but maybe the payload wants to be in polar orbit and they don't launch straight east. They launch, in some other trajectory that eventually puts them in a polar orbit. We're in a polar orbit. The satellite's going to be flipping over. Okay, that's one little bit of a problem. The other problem is it's stable on the axis of the magnet. It's not stabilized rolling around the magnet. So you might naively think, and I don't mean that as in a pejorative way, because believe me, as some famous scientist said, an expert is a person who's made every possible mistake in a given field, and that is me, right? You might naively think, because I once naively thought, problem solved. No, the satellite is free to rotate around the axis of the magnet, except it won't. And why won't it? Because when it's spinning around the axis of the magnet, it becomes a gyroscope. And what I just said was that axis is constantly changing. So you have a gyroscope in your hand, and you're constantly trying to move the axis that the gyroscope is spinning on. When you do that, as you probably know if you played with the gyroscope, it will develop a torque that's the cross product of those two things, of the spinning moment, the angular momentum, and the torque that you put on it, and it will create its own torque. Okay, but the magnet won't let it do that motion. It won't let it turn sideways because the magnetic field is saying, no, I'm pointing along the Earth's magnetic field lines. And what that will end up doing is damping out the rotational motion. It won't rotate, right? Because it can't rotate. Because when it tries to rotate, it becomes a gyroscope. The gyroscope wants to be rigid, and the magnet keeps forcing it to point at the Earth's magnetic field. It won't let the gyroscope stay rigid, pointed along one axis. And that causes friction in the gyroscope, you might say. And that friction manifests as moving the magnet off of the pole and the magnet moving it back, and you get this fight between the mechanical and the magnetic. And that will eventually steal energy from that rolling motion, and it won't roll. That's the good news. It won't roll. After a while. It can't roll. But you don't know what axis it's going to stabilize on. That's why I said to you, well, put the camera out the front and the back. And so you don't care what's up and down. You only care what's frontwards and what's backwards. Frontwards will always be frontwards, except when you're going over the North Pole and the South Pole. At that time, frontwards will be straight down. So a magnetic stabilized satellite points in the direction it's going if you're over the equator. It doesn't point in the direction it's going when it goes over Canada, when it goes over Tierra del Fuego, when it goes over Siberia. It's pointing straight down in those situations. So maybe you don't care. Maybe you're going to take your picture when you're over the equator and you don't care. It's fine. You don't have to care. But you just have to know that it isn't pointing horizontally. The Earth's magnetic field is not parallel to the surface of the Earth anywhere, really. I mean, maybe one point it is, but that's kind of an idealization, and you have to keep in mind that it is an idealization. So that covers all the pros and the cons. This is much simpler than gravity gradient stabilization. Thank goodness, right? I can make one peripheral comment on this. Every satellite is a magnetic stabilized satellite. It's impossible to create something out of metal with electricity flowing around it that has a zero net magnetic moment, right? Every satellite, we try to make it zero because this is going to be another big disturbance torque. Magnetic and gravity gradient torques are huge compared to the other torques you have in space, like solar pressure or solar wind. There's just nothing up there. If you're at 700, 800 kilometers, there's nothing up there. It's virtually torque-free motion, and the things that really wipe you out are gravity gradient torque and permanent magnets. So we try to get the moment of inertia tensor as close to equal on all three axes as possible to get rid of gravity gradient, and we try to clean up the satellite so it has no net magnetic moment. That is easier said than done, because, okay, you can make a rule. No magnetic materials on my satellite. Don't do that. Nothing of iron, nothing of steel that contains iron. The trouble is, within your chips, they have stuff, right? And you'll say, well, that's pretty nano. But if a lot of chips have it, it may not be nano. A bigger source is that you have current flowing through wires. And if that current makes a loop, that's going to create a net magnetic field that'll interact with the Earth's field and create a torque, right? So what I like to say is we don't have negative ground on satellites. We don't just attach wires to the plus end and let the current go wherever it wants to get back to the battery. No. Everything that's powered is powered by a twisted pair so that you have the plus and the minus, the going of the electrons and the coming back of the electrons have to have zero area circumscribed by that. So there's no loops. Right? So we use twisted pair because essentially that makes a million little loops that are all negative of the one behind them. And so they pretty much cancel out to first order, to second order. Everything has to be twisted. The trouble is that inside of components, they may not be exactly wireable that way because you've got to connect the negative to one side of the transistor, let's say, and the positive to the other side. And so you have a small loop. And the only way to know what you've really got is to turn the satellite on and measure it in a Faraday shield. And that's what we do. And it's kind of like balancing your tires. You make the tire as symmetric as you can. Then you spin it and you find out it's not perfectly symmetric. You add a couple of weights, right, to balance the tire. So what we do on satellites is we add a couple of permanent magnets to balance the magnetic field and try to zero it out. The trouble with doing that is that the magnetic field isn't always the same. It depends when the radio's on and when the radio's off. Right? If you have some big load like a heater, that may tend to make a magnetic field when you turn it on. Or if you have a motor, a stepper motor, you're going to open louvers and close them. You're going to deploy, a system and then undeploy it. When you're doing those things, you may create. So then you have to decide, well, what's the most visited state of the satellite and zero it out for that one and just accept the fact that you're going to have disturbance torques when you do all the other ones. So that's the other reason that magnetism is super interesting because, again, like gravity gradient, very few people fly magnetic stabilized satellites. Very few people fly gravity gradient satellites. When you work in the big satellite world, they don't do that stuff. But they know all about it because those are their disturbances. Okay, so we can go on to slide 20, which I put in there. I left it in there because I made this little advertisement for Space Horizons when we did a Space Horizons on going to space to save the Earth. And I made this kind of cartoon of the Earth made to look a little bit like Venus because I think one day the Earth will look a little bit like Venus. And, this kind of hazy UFO that comes in and says, may have at one time supported primitive. That's how we talk about Venus. One day they're going to talk about us the same way. I mean, we don't care because we're going to die before them, but that's not much of an attitude. And getting there is not going to be pleasant. The transition from a nice blue planet with photosynthesis going on to provide oxygen to us. I mean, that it's a nice place to live. So anyway, I won't dwell on it. You all know that. I have another note in here about a homework. I'm going to skip over that for right now, the homework 2. But anyway, let me go to, this is kind of a break, to talk before we get into the other forms of stabilization. Talking about unstabilized satellites and gravity gradient and so on, why they still matter. I've been talking about that, so we know why they still matter. The American football stabilization is spin stabilization. I think everybody knows that. Though you could say, well, sometimes it goes end over end, right? Usually when they're kicking the football, it goes end over end. But that's still spin stabilization. I mean, it's just spin stabilization on the other axis. That axis is the stable axis. That's why when you screw it up with a football, it will tend to spin end over end, because that's the maximum moment of inertia. That's where spinning things like to spin, on their maximum moment of inertia. The axis that this quarterback puts into it very carefully, when he throws the football and it goes kind of, the way you think it ought to go, something like a submarine goes through the water. That's why they have the laces on the football, so that the quarterback or who's ever throwing the football can exert some spin on that axis, which stabilizes the football for a while, not permanently. A football in space will not continue spinning the way the quarterback wants it to spin. It will eventually spin the way a field goal spins, because the natural tendency of things, which is a cop-out kind of a phrase, so let me put it another way. The stable spin axis, and you can show this analytically, and actually I got asked it on my qualifying exams for my master's degree, which is a little unusual to even have qualifying exams, but Stanford was like that, is you can show that that's the minimum energy state of the football, flipping over end. How does it make the transition from one to the other? Through disturbance torques. What kind of disturbance torques? Usually aerodynamic torques. Football is not perfectly symmetrical. The quarterback doesn't throw it perfectly symmetrical, and in any case, it goes through a parabolic trajectory, and it's spinning. It doesn't want to change its spin axis, and yet its trajectory is changing as it goes through the air. So as it starts to, let's say, come down, it's getting loaded from the bottom, not from the direction that it's spinning in. So it's a gyroscope, and that gyroscope is being torqued by the aerodynamic torques. That will start to make the football unstabilize, and because it's losing energy to the air, it will eventually seek out its lowest energy spin state, which is end over end. So you can throw a good football, right, with a nice torpedo-like spin to it, and as you watch it in the air, you'll see it go unstable. Usually if you've got enough spin on it, it won't get totally unstable. But little kids throw footballs without spinning them, and they end up, end over end. You know how that looks. When you have too little spin on the football, it doesn't stay that way. This is a problem with rockets when you launch them, right? Because you're launching them like the way a quarterback throws a football, with the thin axis pointing in the direction you want to go. That is not stable. And so there's a lot of work that we have to do to keep rockets stable. Otherwise, they start to pitch over like a football, and they want to be flying, spinning end over end, like the way they look in a field goal kick. So, the football is fantastic as a model of the way satellites stabilize or don't stabilize. Okay, spacewalk stabilization is fairly easy. Obviously, the person is not spinning. They're not gravity gradient stabilized. And, they don't have magnets. So what do they have? They have the Rick Fleeter system from my original slide, slide number, where was it? Slide number 12, the lure of the simple life. They have two thrusters to create a thruster pair to make a perfect torque on every axis. So they can make a perfect pure torque on the x-axis, y-axis, z-axis. You want to think of your body as being split into axes. And so maybe you call, however you want to do it. The x-axis could be, if you spread your arms out, extend your arms from your left fingertip to your right fingertip. That could be the x-axis. Then the y-axis would be from your toes to the top of your head. And then the z-axis would be going from your chest to your back. If that's exactly an orthogonal axis system, No, it would be going from your back to your chest. Whatever. You get what I'm talking about. And what powers those thrusters? Nitrogen, which is what I call the whipping cream propellant system. You got regular compressed nitrogen in a tank, like a scuba tank, like a little scuba tank. And that creates pressurized nitrogen that runs out to all those thrusters. They're usually on the backpack. And he can trigger them. He or she can trigger them to get whatever kind of torque they want. And you can also use them not as perfect torque couples and move yourself up, down, left, right, back and forth. So, your life depends on those things. Obviously, if you're not tethered and you're really free up there, which very often you are, because otherwise the tether would get tangled in a million things. It would be worse than not having the tether. You are relying on those nitrogen thrusters, using them for torque and using them for net propulsion so that you don't get lost in space like that terrifying scene in 2001, The Space Odyssey. That so spooked me when I was a little kid that, I maybe that's why I never wanted to be an astronaut. I just pictured myself floating slowly away, and of course that didn't happen by accident. That was Hal, killing off one of the crew members, but nonetheless, that's how we stabilize astronauts. How do we stabilize the International Space Station? A lot like the Hubble. You have a lot of wheels, spinning wheels, and you spin them up and spin them down to add and subtract momentum, angular momentum from the space station. Those wheels eventually become saturated because there's tons of gravity gradient torque and there's aerodynamic torques, and those torques are going to add up over time. Then we have hydrazine propulsion, monopropellant propulsion system. You use that propulsion to create a huge torque. And the wheel says, oh my gosh, I've been correcting this other torque, and now I'm seeing this huge torque in the opposite direction. I've got to slow myself down, slow myself down, slow myself down, and maybe even spin in the opposite direction because I've got this huge, quote-unquote, disturbance torque acting on me, which is firing those engines. Then the engine shut off, and it's like, okay, everything's fine now. Oh yeah, there's a little bit of gravity gradient torque. I have to start spinning up again a little bit. And you just go through that, what we call saturating the wheels, and then desaturating them with an external torque, which is from propulsion. And then SpaceX comes up every month and gives you more hydrazine. And that's how we stabilize. Talking about sustainable space, the space station is totally sustainable as long as, the Falcon 9 shows up on time every month with air, with rocket propellant. So, then we talked about the moon stabilization and, what wears out. On the moon, we're wearing out. The ocean and so on is what's wearing out. What wears out in normal stabilization systems are mostly the wheels and the rocket engines, which is another reason, gravity gradient with magnetic torque, magnetic hysteresis rods, pretty nice stabilization. Okay, I've got a slide here to kick us off into spinning satellites. And I'm going to just kick us off into spinning satellites, and then I'm going to quit. I feel like I skipped one. I did skip one. Oy. Okay, we won't go into spinning satellites. I'm really sorry about that. I went from slide 18 to slide 20, and I didn't go through slide 19. You're probably sitting there going, Rick, you skipped 19. Okay, let me do 19. I'm sorry about that's just as well, because I want to do the spinning as its own, its own lesson. Okay. 19, I think, was your previous, so you guys know all about this now because you already knew enough about it to decide you didn't want to do it, right? And what's pictured, that little cartoon, is the satellite that, I worked on, 3 of them. And this was before I started my company. I think I started working on them in 1986. I left the company, they were done. Had been done for quite a while. We're waiting for launch on the space shuttle. The space shuttle governed a lot of my career because before I got that job, I had the offer. I was all set to quit my old job and go there and build these satellites. And the Challenger accident happened, and there was no space shuttle for 2 years. Actually, that was a lucky thing. I stayed with my old company, which was a gigantic aerospace company, for more time. They liked me better. I got a lot more experience. And by the time I left, I was so entrenched in the big company that I didn't quit. I didn't have to quit. They gave me a leave of absence to go to the little company, saying, when you're done working for the stupid little company, you can always come back to Redondo Beach. And that, I felt good about that, because I really didn't know if this little company was going to make it. And in fact, in the end, the big company bought the little company. So it was sort of a happily ever after story. But at the time, I was super frustrated. I was all set to sell my house in Southern California. Anyway, it was, kind of an episode for me in life and for my wife. So anyway, the satellite had to fit in a cylindrical accommodation in the back of the space shuttle. And when it got onto orbit, it deployed a boom, and on the end of the boom was that little tail feather, we used to call it. It was actually a few panels, and it made sort of a radar reflector also. It had a lot of right angles in it, the way we built the deployable, so that they could find it from the ground. And it flew at, the space shuttle type altitude, which is not very high and not as high as your satellite is going to go. And so the stabilization of passive aerodynamic was super strong. Okay, it's a fantastic, I'm really sorry you guys are not going to be able to use it, and I'm still wondering, is it really true? And I'm probably going to want to argue with you about it. It is fantastic. Nobody uses it on purpose. A lot of people use it by accident, because as your orbit decays, you're eventually going to get to the point where aerodynamic is way bigger than everything else, right? So at that point, you are aerodynamically stabilized, whether you want it to be or not, unless you're a basketball, which very few satellites are basketballs. They have solar panels and they have antennas, and sooner or later they're going to figure out what's the most, what's the dart-like way to fly through the air. They're always pointing along the velocity vector. They don't flip over. For the same reason, they do not roll around. They can't roll around, because if they roll around, they create a gyroscope. The satellite is constantly pitching, let's say down in this photo, to keep itself aligned with the velocity vector. So because it has to, turn itself around 360 degrees every orbit so that it's always pointing along the velocity vector, so it won't permit the gyroscope to make it spin. And, dissipative forces will take care of that. And, it's passive, it's strong, it's not a wimpy thing like gravity gradient torque. And the pointing in low Earth orbit, when, talking about space station or space shuttle, when we used to use the space shuttle to get to the space station, is super tight, a couple degrees. And I can tell you from the photos and the telemetry we got from the satellite, it stabilized when it was still in sight of the space shuttle. I mean, it was stabilized in 30 seconds. It was a fantastic stabilization system, and everybody loved me. I was the AOS guy on that, the ACS guy on that, and I had done absolutely nothing. I had done a back of the envelope calculation. Okay, if we put it 30 centimeters or half a meter behind us and it's this big, it'll be super stable. Don't worry about it. Just deploy it reliably. We're golden. That was pretty much it. On other gravity gradient satellites that had to flip over, I spent a year and a half of my life with consultants, with a team, blah, blah, blah. With this, it was like you could do it one night and come into the office the next morning. It worked fantastic. The yaw is damp but not controlled, right? It doesn't work, very high up. And it's making more drag, which is, where is that drag coming from? It's coming from your orbit, right? I mean, it's decaying the orbit. Luckily, this was a very quick mission, less than a month, so we didn't care. It requires a deployable, and it theoretically needs to be damp, but not really, because the aerodynamics itself damps it. So that was probably the part I spent the most time on, was calculating whether it needed damping. In this particular case, we had a liquid on board, so it really didn't matter. Then there's a 1/2 rho times the area times the drag coefficient times the velocity squared times the distance between the center pressure and the center of drag. That's the formula for how much torque you're going to produce. It comes from the airplane world, basically. And if you'll notice, it's 1,000 times bigger than gravity gradient. 1,000 times bigger. Gravity gradient just doesn't enter into your world. So it's a very simple system. It points the direction you want to go. I'm super disappointed that you couldn't make it work out. I think it might be simpler to make a bigger drag device on the back and try, okay, the air is rare, as they say, at 500 kilometers, but it's not zero, and maybe it's just a matter of getting twice as much area or 4 times as much area. I don't know. I really don't know. But I'm not giving up hope, until I talk to you guys about it. So I have the little illustration of the guy with the super pipe wrench, because aerodynamic is a super pipe wrench. Eventually, it takes over everything, and when satellites re-enter the Earth, the last thing that they are is aerodynamically stabilized. They're not spinning around out of control like the public thinks they are. They're just like a dart that you throw in a bar, right? They are absolutely pointing in the direction that they're going. Okay, so this is a good breaking point at 35 minutes. And I've really covered, maybe in a very superficial way, maybe in a very verbose way, maybe not in the way you would have liked it, which is why you have the Wirtz book and why you have my textbook. What I'm trying to do in these lectures is tell you what it's like to engineer these systems. I'm not trying to plow you through, blackboards full of equations. The blackboards full of equations are in books. And, when you want to do this, if it's your job to do a simulation of whatever it is, same thing with thermal. I'm not going to walk you through a spreadsheet to calculate thermal equilibrium. It's just not a good use of your time listening to my voice. I can do it top level, but, if we plow into it, we're going to spend, weeks on stabilization. And this class, it's just not about that. What I'm trying to give you in this class is a sense of why we do X instead of Y, or what's the trade-off between X and Y, so that little lights go on in your brain when your boss says, oh, what about gravity gradient? And you're like, oh yeah, Rick said this, Rick said that. That, I hope, will stick with you. That's what my boss here in Rome, the chairman of my department, calls, the rules of thumb. This is what I'm giving you, are the rules of thumb about stabilization. Even the rules of thumb take, 4, 5 podcasts to cover. And, I studied this at Stanford for my master's degree. I was there approximately a year and a half, taking like 5 courses per semester, and I didn't know anything when it was all over. So, it's a big subject, and we're trying to compress it into basically a week of classroom time and podcasts. So those are my excuses for being, a little bit superficial. On the other hand, I would say my approach to engineering, personally, my value add is in the intuition more than in the analysis. Sure, I've done the analysis, and every working engineer does a lot of analysis, and I've certainly done that. But I think my main value add as a systems engineer is I have a good intuitive feel for what's going to work in what situations and what's worth the trouble and what's not, and then can go and do the calculations and do the quantitative trade-off. But I think as a systems engineer, what you want is the intuition. How does this feel to me? So it guides your analysis. If you have to analyze every possible case, you're never going to get there. It's always a combination of human and machine. And the human part is to say, I'm going to look at this solution first. Think of how you learn to do partial differential equations. You have tricks, and your professor knows. He looks at an equation, he says, this is, I think, the way to solve this equation is X method. And then he plows through X method on the board. What's in my mind is, how did he know to go to the X method? So then I'll say to him, sir, how did you know to go to the X method? And it's like, because I've solved 8,000 of these, I've been staring at these problems all my life. I have developed an intuition, and that guides him. If it doesn't solve it, he's going to scratch his head and he's going to go, well, maybe I should have used, the B method. And then he'll try the B method, and okay, well, in that case, I hadn't anticipated, but the B method is more, efficacious than the A method or the X method or whatever it is. So, that's where we're going with this whole course. So anyway, I'm going to quit and go on to handle the spinning cases last, which covers everything. At that point, we've done everything. Then I'm going to clean up a few details about, the realities of how we do, actually build and test these systems. And then we're done with ACS, which is basically a week of, a solid week of the course usually. Okay, talk to you soon. Bye.